Like we did last time, we went through an SOFC system and thought about the recuperative heat exchange. Let's go through a PEM system and try to think a little bit about the water management and what this process might look like. So first of all, let's imagine our PEMFC. Again, I'm going to think about this as a black box. So imagine we have a PEFC stack. These run at different temperatures, but typically they're below 100 C because we want to not boil away all the liquid water. Let's imagine we're at 80 degrees C, just for this example. So here's our PEFC. I'm going to imagine a cell voltage of 0.7 volts. The other thing is about utilization. So in SOFCs, we've talked about utilization. One of the big differences between an SOFC and a PEFC, in an SOFC, if you don't burn all the fuel, there's not much else you can do with it. You can't recycle it easily. And that's because the water that is the product of the reaction, that actually appears on the fuel side in an SOFC because the oxygen ions are moving, not the protons. Even if you could separate the water and the hydrogen, how do you take a gas that's at 1,000 degrees Kelvin and recirculate it? In a PEFC, you have more options. If you don't burn the hydrogen, since the water is not produced at the same side as the hydrogen, you can sometimes even dead end a fuel cell. So the hydrogen just goes in and it's consumed. At a minimum, you can recirculate it. So if you ran like 90% single pass utilization, you just take the hydrogen that you didn't use. The only thing that's happened, it's changed humidity content. That's okay. You're humidifying the hydrogen anyway. You just recirculate, recycle the hydrogen back to the feed. So it's not difficult to get an overall process utilization of 100%. I'm going to assume a single pass utilization of 90%, and we'll come back to what that means. So we're going to feed into this thing some hydrogen. The other problem we have is humidity. One of the things I mentioned earlier is every time we make a proton, we're dragging water through. That water has to come from somewhere. So you can't just feed in dry hydrogen. Otherwise, the membrane will dehydrate. So instead, we're going to actually feed in a mixture of H2 and H2O to make up for the water that is going to get pulled through. We also want to preheat the gas. We want this gas to be warm at the same temperature as the fuel cell. So if we're running the PEFC at 80 degrees, typically we're going to preheat this gas up to at least 80 degrees. If the gases go in at the same temperature as they go out, how do we provide cooling? In a SOFC, we have no choice. This is done with high flows of excess air. In a PEFC, we have more options. And one of those is to directly cool the stack. And that's usually done with water. So in addition to the feeds of gases, we also tend to run some cooling water. Water will leave at 80 C. Maybe we'll feed that in at 60 degrees C. It's like cooling an engine block of your car. We have this recirculating water, it goes to a radiator, it comes back cooler, and it's constantly sucking thermal energy out. So out of this anode compartment, we're going to flow any excess hydrogen that we don't use. If we're at 90% stack utilization, 10% of the hydrogen we feed in is going to come out. And it's going to come out also with some moisture. And to first approximation, it will come out saturated because it's going to have been in contact with a polymer, which is at 80 degrees, reaching equilibrium. And so it usually will come out close to saturation. Even though we're consuming water, it might be somewhat below saturation, but it'll be somewhere in that neighborhood. And then we're going to recycle it. Anything we don't burn. And then whatever we need to make up, that our 90% of our fuel, that is going to come from somewhere. Usually we preheat that. So this would be dry hydrogen at 80 degrees C, which is being fed from a low temperature source. So this is H2 at 25 C, for example. We heat it up to 80 C and then mix it with our saturated stuff. This is all at 80 degrees C. We'll end up with a mixture of H2 and H2O, 80 degrees C, and then we're recirculating that. And so if we think for a second, if we're using up moisture, we're pulling water from the anode compartment to the cathode compartment, we have to have an inlet of water someplace. And this is done by a variety of different methods. You can take gases and bubble them through liquids to humidify them. That's one way to introduce humidity into a gas. Another way is steam injection, where you have a boiler, you generate steam, and you just put the amount of gaseous H2O that you want into the process. I'm going to think about it that way for the moment. So into this thing, we're going to inject some steam. And I'm imagining it as saturated steam at 1 atmosphere. So 100 degrees C, we generate H2O gas. We mix that with the H2O that we're recirculating, and that produces our gas mixture going into the fuel cell. So somewhere upstream, we've got to have a boiler. And so I'm taking in liquid H2O, and we're feeding it into a boiler. We're generating the steam. And I'll come back in a second where this liquid water is going to come from. Okay, so that kind of outlines the fuel side. We're putting in hydrogen, we're consuming hydrogen, we're recirculating some hydrogen, and we're feeding in water. On the air side, we also are going to come in. So here would be air. On the outlet, we're going to use up some of the oxygen, but the nitrogen will go through. And we also don't want to deprive the cathode of oxygen. So usually we feed the air in somewhat in excess. It's not like in an SOFC where you're feeding like 10-to-1 ratio of air to fuel, or 20-to-1 or 30-to-1. It is instead close to stoichiometric, maybe 50% excess or something thereabouts, just enough to make sure that we're not using up any of the oxygen, all the oxygen at any time. So we've got N2, we've got some O2, and also it's leaving because it's in contact with our membrane. We're producing water at our cathode, so we're constantly just flooding this compartment with H2O. And the gas that we're feeding through is coming to equilibrium with this membrane, which is close to 1 atmosphere, or excuse me, close to saturation. So this is going to come out at a minimum saturated with H2O. And the other thing that could happen, depending on how much water we're cranking out at the cathode, the saturation partial pressure of H2O might not be enough to carry all of the moisture that we're making. There's no guarantee at this point. So let's also imagine the possibility we could be making some liquid as well. So it could be we're producing H2O gas and liquid saturated at 80 degrees, and that's coming out. We'll talk about how to manage that. So this whole thing is going to come out, and then I'm going to try to maybe recover some of that water. So we'll produce a final exhaust, which contains nitrogen, depleted oxygen, and some H2O gas. And then we'll recirculate some water. We don't want to waste water, so maybe we collect some of it in a tank and then recirculate it. And then if we don't have enough, we can add some. So one question you might ask is, what temperature are we going to do this condensation process at? To the lower the temperature we condense, the more cooling we need, but also the more water we're going to be able to recirculate, because we can knock out more and more water depending on how cold we cool the exhaust. Okay, so here's the other issue. We're producing water. We're leaving with saturated H2O. In theory, depending on the situation, it could be all the H2O that's leaving our fuel cell could be water that we make. On the other hand, maybe the saturation pressure depending on the temperature, as we go higher and higher in temperature, the saturation pressure of water gets so high that the water that we carry out with us in the exhaust from the PEM is too much to uh, is more than we're making. So we haven't worked that out yet. We don't know what the flow rate is in the exhaust. This is the PEFC exhaust yet until we sort of sort through the Faraday's law. So it could be we also need to add water to the air. And so let's keep that option open. And again, let's do that with steam injection. So imagine we take our steam injector and we're actually going to have two streams coming off of it, one going to the hydrogen. We definitely have to do that, but it could be that we also need some steam added to the air. And that's going to combine with dry air. And the dry air, we're probably going to preheat to keep it at 80 degrees. So here's air at 25C, and we're going to preheat this. So this is air at 80 degrees. And then this is going to be air and H2O gas because we're going to inject some steam. And then that goes into the fuel cell. You can see this is getting fairly complicated because of the water, right? We've got to deal with how much water is in each of these streams and how do we keep everything humidified. And as I'll show you in a minute, this is a material balance problem. So let me label some streams. This is stream 1. This is stream 2. This is stream 3. This is, I'll call stream 4 and stream 5. And then the hydrogen will be stream 6. Call this one 7, post heater. 8 is the recycle. And then 9 going into the fuel cell. And then coming out of the fuel cell, stream 10. And then the water, I'm going to call this stream 11. Stream 12 going into the heater. Stream 13 is the steam going to the hydrogen. Stream 14, that'll be the stream going to air. And I think that's all. I guess this is 15. This is 16. You can see where the energy is coming into play. We've got cooling loads. So we have a direct cooling load on the PEFC. We have to have coolant. We have to have water recirculating to a radiator. So this is H2O liquid. It's recirculating to a radiator. We may also need cooling at the condenser, where that question mark is, over here. So this has a cooling duty on it. This has a cooling duty on it. We have electric heaters here. We have an electric heater here and one here. My intuition is this one that we're using to boil water. That's by far going to consume the most power because we're boiling liquid. The others are just relatively small gas streams that we're heating by a modest amount.
At this point in the lecture last year, I went through a long series of material and energy balances by hand to kind of work out what was going on in this flow sheet. This year, what I'd much rather do is go through a spreadsheet calculation of the same thing. I think it's much more straightforward. And that will be the subject of the next video. Before showing you that, though, a few changes from the flow sheet that I presented last year that make it a little bit easier to handle in a spreadsheet. In the previous version, streams 8 and streams 2 came in at 80 degrees C, and thus when they were mixed with 100 degrees C steam, resulted in temperatures higher than 80 degrees C going into the fuel cell in streams 9 and 3. Rather than do it that way, here the temperatures in streams 3 and 9 are 80 degrees C, and we're letting streams 8 and 2 be slightly cooler than 80 degrees C, so that when mixed with steam, they hit the target temperature of 80. This is not really a much practical consequence, but it does make the calculation somewhat easier when implementing it in an Excel spreadsheet. The other change here is that the cooling water is at 40 degrees rather than 60 degrees. This makes it a bit easier when we're talking about the condenser. The condenser is operating in the vicinity of 60 degrees, and so we need something a little bit cooler to be able to drive the cooling there.